Okay, so it's 2:01 p.m. on my computer. So why don't we get started, especially because Aaron has to leave shortly after Oliver's talk for his teaching. Welcome everyone to the first TEPS seminar of the 2020-2021 academic year. I know this is a difficult time for everyone, so thank you so much for joining. And I'm glad that we at least have the technology to bring people together in spite of all the circumstances. So for today, we have three trainees giving talks. So Oliver, Boodram, Olivia Lim, as well as Alex Inanen. So what we'll do is each of you are going to give about 15-minute talk, followed by about 5-minute Q&A. And I will let your advisors introduce you so that you get more exposure.
Okay, I want to start by first thanking Eve and Ahmad for organizing everything here. It's no small task to do all of this, so thank you very much for that. It is my pleasure to introduce Oliver Boodram, who worked with me and Brett Gladman over the summer. He comes from the University of Alberta, where he is working where he's in his 4th year as a honors student in the astrophysics program. Now, over the summer, he just exceeded our expectations. He's done an excellent job looking at the dynamical stability of planetary systems and analyzing their dynamics. I think he has a very bright future ahead of him. So I'll just go ahead and stop there and let Oliver take it away. Thank you, Oliver.
All right, let me just see if I can share my screen here. Here we go. Can you guys see that? Is that?
Yep. Yep, looks good.
All right. Awesome. All right. So hello, everyone. My name is Oliver Boodram. I am an undergraduate TEPS trainee under the supervision of Professor Aaron Boley and Brett Gladman. Today, I'll be talking to you guys about the dynamics of multi-planet systems. There we go. So what is so strange about the observed population of multi-planet systems that we see today? Well, from the Kepler mission and its observations, we see a variety of planetary structures, types, and architectures that are very different from our own solar system. In particular, there's one abundant system, the tightly packed interplanetary system, or STIP, as I will abbreviate it as, and that will be of primary focus in this presentation. Now, to get an idea of what a STIP actually is, I would direct your attention to the bottom image of this slide, which effectively just illustrates the planetary separation or planetary separations for two different systems. The top line represents a STIP, and the bottom line represents our own inner solar system. As we can see in the STIP, there are 6 planets, and out of the 6, 5 are within the Mercury-Sun distance. On top of that, these planets are very close together. So we can see it's very different from our own solar system. And for that reason, it's of great dynamical interest. Now, although we observe a bunch of these STIPs, we still don't know everything about them. Obviously, we're limited by our observational techniques, and it is possible that other planets could lie in these systems that we don't know about. Now, that kind of leads into what I did this past summer, which is where I examined the stability of STIPs in the presence of unseen or undetected outer planetary systems. Now, hopefully the results of my project could give some sort of insight into the plausibility of the existence of these outer systems around these STIPs. For instance, if I simulate a bunch of outer systems, I find that they cause the system, the STIP interior to them, to implode and go completely unstable. Then it's unlikely that the stable observed STIPs that we see today have these outer systems. So just to start and review some theory and some background, I want to just review the basic Keplerian orbital elements. So on the top left there, we can see that there's the familiar semi-major axis, which represents effectively the size of the orbit. And in the bottom left, there's the eccentricity, which represents how elliptical an orbit is. On the right, there's a bunch of parameters. To start, I will highlight the inclination, which represents how inclined the orbital plane is. with respect to a reference plane. And due to that inclination, there's an intersection between the two planes, which is known as the ascending node. Now, the longitude of ascending node is referred to as the angle between some reference direction and that ascending node. And the argument of periapsis is the angle between that ascending node and the direction to closest approach of the celestial body, or direction to pericenter. Finally, the true anomaly is defined to be the angle between the direction to pericenter and the celestial body's current position in its orbit. Now, how exactly do these outer systems actually make these inner systems, or these STIPs, go unstable? You know, even if we look at our own solar system, we have Jupiter and Saturn, Uranus and Neptune, and those are quite massive. Yet they're so far away from planets that could be potentially within Mercury's orbit. So shouldn't their gravitational tugs be kind of weak? Well, actually, there's a lot of dynamical phenomenon that outer systems can induce on inner systems to influence their stability. In particular, or actually, no, sorry, I will get into more of those in the rest of the presentation. But just to illustrate the concept, I want to highlight the results from this paper, Mustiel and al. 2017. They simulated a hybrid planetary system where you had an inner planetary population and then a large separation and then an outer planetary population. The two seemed relatively disconnected and well separated. However, they found that whenever there was an instability in the outer system, an instability soon followed in the inner system. So this implies that there's some communication or interaction between the two systems that is not super trivial. So the theory that sort of governs these interactions and these effects is known as Laplace-Lagrange planetary theory. Now, in my project, I used a linear approximation or low order form of the theory known as linear Laplace-Lagrange planetary theory. Now, under this approximation, eccentricities and inclinations can actually be represented as vectors. Now, if we look at the top left of the slide here, we can see a parameter omega bar, which is equal to the sum of the longitude of ascending node and the longitude of argument of periapsis. Now, this omega bar is called longitude of pericenter, and together with the eccentricity magnitude, those two values form the polar coordinates for the eccentricity vector. And with polar coordinates, there's corresponding Cartesian components of that vector as well, denoted as k and h. Now, you can do a similar thing with inclination as I show on the right, but I'm not really going to get into it too much. I'm just going to talk about the eccentricity components. Now, these eccentricity components can be written under this theory, this linear theory, as a linear combination of normal modes. Now, what exactly is a normal mode? Well, if we call back to our undergraduate mechanics course, we should recall the coupled oscillator problem. In this problem, we could effectively describe the displacement of any of these masses as a linear combination of oscillatory terms that oscillated at the natural frequency or eigenfrequency of the coupled oscillator system, and had amplitudes proportional to the eigenvectors. In a similar sense, these eccentricity components can be written as a combination of sinusoids that oscillate with the eigenfrequencies of the planetary system. So how exactly, though, do planets go unstable? There's a bunch of ways, but the one that's sort of supported by this linear theory and that I will focus on mostly is secular resonance. Now, what exactly is a secular resonance? Well, if we think back to the coupled oscillator problem, if you force one of the masses in that system at the system's eigenfrequencies, it oscillates with maximum amplitude. In an identical manner, a secular resonance is simply just a location away from the host star where you place a planet there and it's gravitationally tugged on by the other planets in the system such that it is forced at one of the system's eigenfrequencies. This leads to maximum eccentricity oscillation in one of the normal modes. Now, what happens when you have large eccentricity oscillations? Well, you can have orbits that intersect or cross each other, and that can lead to close encounters between planets, as well as that can lead to mergers between planets. And that's what I define instability in this presentation to be, which is mergers, planetary mergers. Now, how exactly did I evaluate STIP stability? Well, I effectively simulated a variety of planetary systems. Now, to do this, I used an n-body integrated Python package known as Rebound, and rebound-x, which is another Python package that contains a library of planetary dynamical effects. Now, for the planetary systems that I simulated, I modeled the inner system, or the STIP, based off of 3 observed STIPs. And so I would generate essentially 3 sets of simulations for each variant of the STIP. So the 3 STIPs that I based my simulations on were Kepler 11, K2138, and TRAPPIST-1. Now, why did I use these particular observed STIPs? Well, I just wanted to make sure that the dynamics I was studying applied to some relevant region or corner in the universe. Now, although these STIPs are detected and observed, we still don't know all the orbital parameters about them. So we tried to take as much as we could from the known recognized NASA exoplanet archive, but when certain orbital parameters or maybe masses weren't known, we'd have to randomly sample or generate them. Now, our first step that we had to do is we effectively had to make sure that our STIPs remain stable by themselves. Now, the reason being is if we can show that our STIPs are stable by themselves, and then we add an outer system, and then the outer system causes the STIP to go unstable, it is likely that the outer system induced some sort of instability, since we know the STIPs are stable by themselves. Now, what exactly does a stable STIP look like? Well, it sort of looks like this plot here. Now, each of the different colors represents a different planet in the STIP, and on the y-axis we have AQQ, and on the x-axis we have time. But what is AQQ? Well, A represents the semi-major axis of the planet. Uppercase Q represents the distance, the furthest distance that the planet can get away from its host star, and lowercase q represents the closest distance the planet can get to its host star. As we can see in this plot, there are no orbit intersections, as each of the planets are bounded to their own sort of unique intervals in space. Now, this is what an unstable system looks like. As we can see, it is indeed very different. We can see that, for instance, maybe it might be kind of hard to see, but the blue planet actually sort of bleeds into the green planet's area, and they actually merge together and form one resulting planet. On top of that, we can also see that there are just these large or more excited oscillations in apocenter and pericenter distances. So these are all signs of a highly excited system, and this is what we don't want for our STIPs. We want them to be very stable. So once we got our STIPs to be very stable, we effectively need to we had to choose an outer system. Now, how exactly do we choose an outer system? Because there's so many options. You know, we could have 4 Jupiters, 20 Saturns, where the third Saturn semi-major axis is reduced by a factor of 2. You know, what do we pick, right? So we had to pick an outer system with some dynamical significance. So our first choice is we decided to go with our own outer solar system, that being Jupiter, Saturn, Uranus, and Neptune. And so for our 3 STIPs, Kepler 11, K2138, and TRAPPIST-1, we would place an outer solar system exterior to each of them, and we would simulate them for a long period of time. But what we found was that the inner system stability was actually, the systems were completely stable with or without the presence of this outer solar system, which sort of implies that the outer solar system isn't really doing much to influence the stability of these STIPs. Now, with the results of those simulations, we decided to target and try and induce more dynamically specific phenomenon onto our inner systems by modifying our outer systems. Now, specifically, we wanted to see what happened when nonlinear dynamical effects effectively dominated the dynamics in our inner system, or our STIPs. And that happens when the linear theory, or the linear approximation that I talked about, breaks down. Now, when does this linear theory break down? Well, it happens in particularly 2 regimes. So the first question we want to see what happens is, when do 2 of the n eigenfrequencies become very close together in magnitude? The corresponding 2 normal modes, then, when they constructively interfere or add together in that linear combination, they can actually beat together or form wave packets. And when you have that in your eccentricity evolution, that can lead to nonlinear dynamics effectively dominating your system. The second thing we want to look at is what happens when one of the normal modes oscillates with a very large amplitude. Whenever there's any sort of large eccentricities involved in the dynamics, the linear approximation also breaks down and nonlinear effects start to dominate. Now, before we got to test those 2 questions out, we had to modify our outer system just a bit. And so we decided to remove Uranus and Neptune and just keep Jupiter and Saturn. The reason being is we wanted to, one, make things computationally less expensive and faster. And also we wanted to be able to really understand analytically and theoretically the dynamics going on in this n-body problem. So regarding our first question, we wanted to get two frequencies that were close together. Now, unfortunately, due to planetary separation constraints, we could only use Kepler-11 as a STIP to test this question. Now, what did we do? We generated 100 simulations. In each simulation, we placed Kepler-11 into it. Then we'd place Jupiter exterior at its solar system semi-major axis. And then we would vary Saturn between 8 and 9 AU. Now, why would we vary the position of Saturn? Well, if you think back to the coupled oscillator problem, if we tweak the masses or spring constants in our system, the eigenfrequencies change. In an identical manner, if you tweak the masses or planetary separations in a planetary system, the eigenfrequencies also change. So that's what this plot here is just showing. It effectively shows the magnitude of the eigenfrequency on the y-axis and various locations of Saturn on the x-axis. And we can see that when Saturn is varied between this range, the blue and green eigenfrequencies become very close together, which is what we want. So what happened when this special type of constructive interference or beating occurred, or at least we thought? What happened was that the Kepler-11 STIPs remained completely stable whether or not these Jupiter-Saturn pairs were there. And this was quite a surprise because once again, we expected nonlinear effects to dominate in this regime. And we're still not too sure why, but perhaps from a linear point of view, it is possible that when there was constructive interference between the two close frequency normal modes, one of the normal modes had a much smaller amplitude than the other. And that's what this plot here is trying to showcase, which is where I take the Fourier transform of the eccentricity evolution of these planets. And I can see that there are two distinct peaks where the rainbow colored STIP planets peak at one frequency and the outer planets peak at a different frequency. Both these peak frequencies are involved in the eccentricity evolution of all the planets, but there's power lacking in the rightmost frequency, implying that these two close normal modes, the rightmost one had a lower amplitude. Now, for the second question I wanted to examine, I effectively migrated Jupiter and Saturn inwards. And as we know from before, if planetary locations are changing, the eigenfrequencies are changing. But furthermore, the locations of secular resonances are also changing because the locations where you need the precise tugging to get forcing at an eigenfrequency is changing as eigenfrequencies are changing. So what we want to do is move a secular resonance on top of one of the locations of our planets. That way, the planet's eccentricity would oscillate with maximum amplitude. Now, luckily for us, a previous paper sort of looked at a similar situation with Kepler-11, Granados-Contreras et al. 2018, where they simulated Kepler-11 and then migrated Jupiter inwards. And they found that when Jupiter reached a location of about 0.98 AU, it put a secular resonance right on top of the location of Kepler-11b. Now this plot's just featuring amplitude versus distance from the host star, and we can see right at the location of Kepler-11b, there's a big spike in amplitude. So we decided to apply this migration scheme to Kepler-11 just to see if we could reproduce the results, as well as K2-138 and TRAPPIST-1 to see if any nonlinear dynamical effects dominated. Now, what did we find? Well, we found that a lot of the Kepler-11 systems went unstable, but none of the TRAPPIST-1 or K2-138 systems went unstable. And we're still not too sure why the Kepler-11 systems went unstable. It might be because of secular resonance made the system go unstable, but we're still looking into that. But the main thing to highlight as well with the Kepler-11 systems is a lot of the systems went unstable only when Jupiter got to that 0.98 AU. Now that implies that there's a whole range of Jupiter and Saturn semi-major axes values between the starting value of Jupiter and then this 0.98 AU such that Kepler-11 is stable. Now this sort of just drives home the main point of my project, or my main conclusion, which is that the existence of a STIP cannot rule out the possibility of an outer planetary system in the exterior regions of the exoplanetary system based on the dynamical considerations we have made. you know, we've tried a variety of outer systems that explore a large fraction of parameter space, frequency space, but we found that the perturbations from these outer systems don't really do much to influence the stability of the STIPs. So with that, I would like to conclude and ask if there are any questions.
All right, thank you, Oliver. We have time for one brief question.
Yeah, sorry if I went over time there.
Oh, no, it's okay.
I have a question if no one else has one, but I'd like to yield for anyone else. Okay.
Wait, okay, so I guess it's more of a comment slash question. So there is a known correlation between the inner super-Earths and the existence of an outer gas giant. But this existence actually starts to fall off once you go to multiplicity of the inner systems beyond the, like 3 and 4. So I'm wondering, like, if you experiment, like I know you focused particular on 3 systems, but I was wondering, like, if you were like thinking of or experimented with the multiplicity of the inner system versus the instability induced by the secular resonance by the outer planets or outer giants.
Yeah, I don't know if we were particularly targeting the effects of multiplicity. I think, yeah, I didn't even realize that there was a connection between the super Earth multiplicity and presence of an outer system. So yeah, I can't say that we did target that. I know that the STIPs that we did examine did have different multiplicities, but yeah, I guess we were just more focused on the overall stability of the STIPs than the particular differences among the STIPs per se, but at least in that sense, in terms of multiplicity. There were some differences that we were looking at between the STIPs, but not multiplicity, I don't think was a main factor. Yeah, sorry if that doesn't answer your question.
No, it's okay.
Yeah.
Just as a quick point of clarification, if I may, Eve, that's for 300 days or so, right? I mean, we have to put a cutoff somewhere.
Right.
I think so. I think it's that 300 days or so.
Sorry,
so it depends on what one means by outer, but yeah, absolutely.
Yeah, exactly. Yeah. Okay, in the interest of time, we should move on. Thank you so much, Oliver.
Yeah.
And
thank you everyone for listening.
And next up is Olivia, and I'll let Renee introduce Olivia.
Hi, my name is René Doyon. I'm a professor at the University of Montreal, and I have the pleasure to supervise Olivia Lim on a PhD. She started about a year ago. And Olivia will be, for her PhD, will be studying a very famous TRAPPIST-1 system. This system has 7 planets, 3 of which are in the habitable zone. And she's going to use a variety of observations to study this fascinating system. And including JWST data and also precision radial velocity from the ground using the SPEW and the NIPS spectrograph. And today she's going to talk about an issue associated with the SPEW instrument, in fact, near-infrared instrument, which is called persistence. And that's something that prevents us from measuring the spectrum accurately. So it's an instrumental effect associated with the instrument, with the detector. And that's what she's going to talk to us about. So if you can take it away, Olivia.
All right, thank you, René. I will share my screen. Can you see this?
Yes.
Yeah, that's fine.
All right. All right. Hi, everyone. Yes, my name is indeed Olivia Lim, and I'm a PhD student at Université de Montréal, supervised by René Doyon. And today I will present a progress report on detector persistence correction with SPIRO. So before we start, I want to give some information about Spirou that's relevant for this presentation. So Spirou is a near-infrared spectral polarimeter at CFHT. Usually people are interested in the final products that Spirou gives, which are spectra, but today in this presentation, we will look at 2D images, the 2D images that Spirou's detector takes, which look like this. In this picture, you can see vertical stripes. These vertical stripes are the 49 orders of Spirou. And if we zoom into this image, we can see that each order, so like these 3 stripes form one order. So each order has 3 smaller stripes. This is because Spirou is fed by 3 fibers, fiber A and B for science, and fiber C for reference. So the 3 smaller stripes within each bigger stripe correspond to those 3 fibers. Now, what is persistence? It's easier to visualize persistence by thinking about what happens when we look at a source of light for some time and then we close our eyes. We can see a ghost image typically. So the human eye doesn't work like an infrared detector, but the observed effect is similar. In a detector, persistence is when the image of an exposure remains imprinted into the subsequent exposures with a time decreasing signal. And in some cases, the signal stays detectable several hours after the contaminating image was taken. Now, what does persistence look like in SPIR data? It looks like this. So this is a set of engineering data that we use to develop our persistence model. This data set has 12 cycles. So each cycle has 5 images taken with illumination, which I call flats, shown in orange. And they're followed by 6 images taken without illumination, or darks, shown in blue. So keep in mind that this engineering data set is actually a series of 2D images as a function of time. This figure shows the flux as a function of time, but the flux is averaged over a certain region of the detector. So this is why we're looking at 1D data points in this plot. So our goal is to develop a model that can predict any dark data point in this engineering data set given all the previous points. And eventually we want to use the same model with its fitted parameters to predict persistent signal at any given time, but in a real science data set given all the previous observations. So to do this, we need a model to describe how the persistent signal decreases over time. We could imagine using, for example, a power law with a negative exponent or an exponential law. But in any case, we have to keep in mind that at any given time, the persistent signal is not just one of these equations. We have to add up terms like these for each previous frame. So in this figure, for example, our model would be the blue curve, the solid blue curve, and not the green dotted curves. So we've been focusing on the exponential law for now. So the rest of the presentation will only show results from this model, but we're not completely ruling out the possibility to use the power law or any other law really. So if we fit the exponential law to the data points of the dark images that I showed earlier, this is what we get. The blue dots are the data, the green circles are the best fit model, and the bottom panel shows the residuals. So if we look at the residuals, we can see that there is some structure, and this structure is telling us that our model is probably missing something. So one thing we can do is just add a second term to the exponential law so that we have 2 different time scales. Like in this equation, we actually parameterized this equation slightly differently. We used this form, which is equivalent, but basically we now have 4 parameters. We have the overall amplitude A, the time scale of the first exponential tau, the amplitude ratio B, and the ratio of the time scales K. And this is the fit that we get when we use this more complex model. So we can see that well, the RMS has decreased, which is not surprising given the larger number of parameters, and we also removed some of the structures. So all that works fine for 1D data points, but we actually want to apply our persistence correction pixel by pixel on 2D images as a function of time. The problem is that there are about 16 million pixels on the detector, so fitting for 4 parameters for that many pixels would be quite long. So as a starting point, we had to fix some of those parameters. We actually fixed all of them except for the overall amplitude. And so to do that, to fix those 3 parameters, we chose 6 representative regions of the detector shown in the green and yellow rectangles here. And we took the average of the flux for each region. So this gave us 6 time series, like the one in the previous plot. And then we fitted each time series by letting the 4 parameters free. So this gave us 6 best fit values for each of the 4 parameters. And then we took the median of the 6 best fit values for each parameter, and we fixed those 3 parameters at their median best fit value. So by doing that, we end up with the amplitude, just the overall amplitude as a free parameter. So our function becomes linear, and it becomes very fast and easy to fit 2D images as a function of time by adjusting the overall amplitude, but this time for each pixel. And so by doing that, we end up with a map of the overall amplitude, the persistence amplitude, and we can interpret this map as a memory of the detector. So for example, if you look at these pixels that are brighter, they have larger persistence amplitude. So that means that they can remember better what illumination occurred in the past. This map only has valid values at pixels that were that received enough flux. So for example, the pixels between the orders did not receive any light, so those pixels are not usable, and this is why all the yellow pixels in this image are not usable. But still, we can use this amplitude map and the other 3 parameters that we fixed to try and correct the dark images in the engineering data, just to see how well our correction code performs. So, okay, you can focus on this image for now, the one on the left. So this is the first dark image taken in the engineering data. So it's the first image that was taken after we stopped illuminating the detector. So we can clearly see the orders, and that's persistence. That's persistence from the previous illuminations. And then on the image on the right, we see the persistence corrected version of that. So we can see that the orders are much less visible, which is good. That means that our correction code is removing most of the persistent signal. Okay, this is the same image, but for a dark that was taken later in time. So there's less persistence because persistence decreases over time. And again, the corrected version of that is very clean. We barely see any orders left. And then again, this is another dark, but that was taken later in time. So all the images that I showed on the right looked clean, and the results are similar for the other cycles of the engineering data. So this looked promising until we tried to correct real science data, not engineering data, using the same amplitude map and the same fixed parameter values as before. So just typically when observing science targets, you don't pause between observations to take dark images and look at persistence like we did in the engineering data. So we had to choose a science data that would allow us to see persistence like we saw it in the engineering data set. So I mentioned earlier that Spiro is fed by 3 fibers, one of which is used for reference. In this reference fiber, fiber C, you can choose to either turn on or off some light sources that produce very particular signatures, One of those light sources is called a Fabry-Perot, which produces these evenly spaced bright lines in fiber C. Okay, and this image on the right is just for reference. So this image was taken with the Fabry-Perot turned off, just so that you can see that in fiber C, it's completely dark because the Fabry-Perot was turned off. So now back to the science data that we had to choose. So we chose an observation that was taken with the Fabry-Perot turned on. And then this observation was followed by an observation with the Fabry-Perot turned off. And the idea was to see if our correction code could remove the Fabry-Perot signal that was persisting from the first image onto the second image. So here on the figure on the left, you can see the observation that was taken with the Fabry-Perot turned off. And you can see some Fabry-Perot lines from that's persisting from the previous image. And then on the right, the figure shows the corrected version of the figure on the left. So you can probably see that the Fabry-Perot signal is still visible in fiber C in this image. So this is bad. This means that the correction code did not do a good job at erasing the persistence from the previous image. And I can also blink between the two images. And if you look closely, you can see that the correction did remove some signal from the Fabry-Perot lines, but not much. I've also tried correcting the subsequent images, which were taken with the Fabry-Perot turned off as well, but the correction did not improve with time. So basically we did all this and realized that our correction didn't really do much on the science data. And so this is our problem at the moment. We can correct this very particular set of engineering data on which we developed our model, but we cannot apply the same model to the science data. And this is very anticlimactic, but we don't have a solution yet. We do have some ideas that we want to explore. One of them is that we don't know exactly how persistence scales with the received illumination. For now, we assume that persistence scales linearly with illumination, but this could be a problem because the flats in the engineering data have very high fluxes of about 350 ADUs per second, whereas the Fabry-Perot in the science data have fluxes of less than about 20 ADUs per second. So maybe by developing our model with the engineering data, we actually end up with a model that only works in a certain regime of illumination that happens to be different from that of the science data. So we need to look into how persistence scales with the received illumination. And once we know more about this, and if there is indeed a clear relationship between illumination and persistence, then we should probably get more engineering data with various illumination levels that are closer to what we usually have in science data. So that's all I had to say, and I can try and answer questions if you have any. Thank you.
All right, thanks, Olivia. We have, again, time for 1 or 2 brief questions.
I would like to ask one if you can hear me.
Yes.
Okay, so you mentioned that persistence might be a function of illumination. How about also the next image that you take with the persistent image? Any reason to believe that new flux on the persistent image would, affect its behavior? Like it would shake the substrate and vanish the persistence quicker if there's new flux? Or is it only the image that was taken to create the persistence, or the new image is also, the flux of the new image also has an implication?
That's a good question. I don't think we have, we've thought about considering the present image affecting the present image in terms of persistence. I don't know the answer to that question. If anyone knows, you're you're welcome to answer.
Well, we don't know. This is a good question, but I hope your effect is not real because we're screwed, Fred.
But I was thinking that maybe there's also a factor of the next one. But yes, sure. Just a question that came up when listening to the talk. Very interesting topic.
Thank you. Thank you for your question.
Any other questions?
I had a question. So with the Spitzer Space Telescope, we've sometimes seen issues like this. And one of the strategies that we used, which I wonder whether would work for something like Spiru, was to like sort of pre-flash the detector by like staring at a bright diffuse target before doing our science observations. Is there any strategy that you could do like that to mitigate this persistence effect, where you're basically purposefully doing something weird to the detector before you take your science observations?
Yeah, I think there's 3 points I could comment. The first thing is we're not absolutely sure if by flashing the detector before doing an observation would help. I'm not saying it doesn't help, I just don't know if it does. The second point is I'm not sure if time-wise, like I don't know if the time allocating committees would think this is a good idea. I don't know how long the flashing would be. And third point is not related to Spiru, but related to NIRPs. I think there's a light installed in NIRPs, and the idea is to illuminate the entire detector in a uniform way in order to reduce the persistence, or at least sort of erase whatever happened before. So if it does work, and if it does work on NIRPs too, that's a good point. And I don't know what else I can say about this.
If I may add very briefly, so it's a very good question, Nick. And in fact, we have data with some lamps that really super saturate the detector, and clearly the persistence is very much different in a way that it's gone. So yes, indeed, and this is terra incognita in this, and for this kind of detectors. And so it's not impossible that this kind of scheme where you would blast the detector really badly could actually cure the persistence. So we have yet to investigate this, but it's a good suggestion. We may actually try that in the lab.
Okay, great. Thank you so much. And